Hello everybody. My name is Smagul Karazhanov. I am Area Chair in the Institute of Solid State Physics in Riga, Latvia, in the University of Latvia. Today, I will tell about adaptive photochromic films for smart window applications. You can find many literature online, and there are many published books on this topic. In addition, you can find many review articles or scientific journal articles in many journals. The lecture includes introduction. There I will say about chemical and physical photochromism, about examples of photochromic coatings, about synthesis methods, characterization methods, and about parameters characterizing photochromic coatings and possible applications of the photochromic coatings. Photochromism, it stands for change of color of a matter under influence of light. Photo, it's light, chrom, it's color. So photochromism, it is change of color under influence of electromagnetic radiation on matter. Here we need to know some terminology. So the optical state of the matter before illumination is on is called transparent state, and after illumination, when material's color is changed, it's called as photodarkened state. Then color change is accompanied by not only changing the color of the matter, but also it can accompany change of refractive index, for example, about wettability, and also electrical properties, for example, in case of semiconductors. As to chemical photochromism, there are today many materials that exhibit chemical photochromism. Under chemical photochromism, we understand change of chemical bonding when under influence of electromagnetic radiation, when atoms, molecules regroup or undergo structural rearrangement under influence of light. Under physical photochromism, we understand changing the population of electronic states in the matter because of light. For example, absorption of light will transfer electron from its ground state to excited state, and then this process is accompanied by color change. So this is what we call physical photochromism. In nature, in fact, both of the mechanisms can be mixed. So there might be that in one material, one mechanism might not be like a pure just chemical or pure physical, but it can be mixed as well. And some examples of photochromism. One of the well-known examples is tungsten oxide-based hybrid photochromic films or molybdenum oxide-based. These tungsten oxide-based thin films, they also exhibit photochromism. Why then we need hybrid films? Because tungsten oxide thin films itself, although they exhibit photochromism, from photodarkened state to bleaching state, this process is not spontaneous, and some energy should be spent for bleaching. For example, heating or applying very high electric field. When the nanomaterials of tungsten oxide is incorporated into some polymers, then this hybrid material, this is called hybrid material, and it will be spontaneously bleaching into transparent state. Here is one of the examples. On the left picture, you can see here transparent material based on the hybrid material. This is before illumination with sunlight. Near to it, you can see these fibers of tungsten oxide embedded into polymer. When it's illuminated, one can easily see these tungsten oxide fibers. These fibers can be synthesized in such a way that it can be nano-size fibers or micro-size fibers as well. And after this process is done, one can deposit thin films of the hybrid photochromic film by different methods, by brushing, by spray coating, by inkjet printing, for example, or spin coating. There are many such methods of depositing the films. And at the bottom, you can see two images of photochromic films based on tungsten oxide. And also tungsten oxide-based hybrid films, and here tungsten oxide is incorporated into PVP and then deposited on glass and onto these sheets of glass. And on the right-hand side, you see transmission spectra corresponding to transparent state of the film and transmittance corresponding to different times when the sunlight is illuminated, when the sunlight is on. Okay, one of the negative points, disadvantage of this material is for, practical applications in Windows. The material blocks visible light. This is negative point. It would be perfect if the material, instead of blocking visible light, if it blocks UV and heat waves, that would be advantageous. And another example of photochromic coatings is Yttrium oxyhydride. In fact, there are many types of oxyhydrides based on rare earth metals also, like they include gadolinium oxyhydride, dysprosium oxyhydride, and so forth. There are many such examples today. Distinct from oxide-based photochromic coatings, these inorganic mixed-anion materials, they are pure and inorganic, and also they will be bleaching spontaneously. This is advantage, and this opens the way toward practical applications of these coatings. So what stands for mixed-anion materials? On the left-hand side, you see this picture. Here, big balls of green color, they denote yttrium atoms. And small radius blue color atoms show hydrogen atoms. So this is matrix of yttrium dihydride. When one deposits such material by any method, if afterwards they expose it into air, the material will get oxidized. Oxygen atoms will enter into the matrix and they will replace partially some of the hydrogen atoms. So the second lattice here indicate the case when some oxygen atoms, 2 oxygen atoms at least, replace it 2 hydrogen atoms. So both oxygen and the hydrogen atoms, they are situated in tetrahedral sites, the same sites, okay? Just these sites are shared with 2 different types of anions. One is hydride anion, the other one is oxide anions. So this is what we call mixed anions. So these mixed anions, they possess such a unique properties that are not available in single anion material. For example, yttrium hydride, it is metal. If one have a look on its electronic band structure, one can notice this is metal. It's black color metal. When and yttrium oxide, when there is no hydrogen inside it, that's ultra high band gap material, which is transparent to visible light. And when 2 anions are hydride and oxide anion, and the band gap of the material will become lower than that of yttrium oxide, and material will possess additional property, photochromism. Such photochromism is not available neither in hydride nor in oxide. So this is just one of the examples that mixed-anion material possess some properties that is not available in single-anion ones. Okay, and such material one can get, as I said, by depositing hydride first, and then by oxidizing it in oxygen-containing environment. And that oxygen-containing environment can be pure oxygen or CO2 environment or humidity, for example. All these gases can be oxidating agents, and even ozone can also be oxidating agent. Here is typical image of yttrium oxyhydride, yttrium hydride, and yttrium. So metallic yttrium is shiny reflective material. Yttrium dihydride is black color, also reflecting material. It is metal, and oxyhydride is transparent to visible light. So it is transparent before UV light is on. And after it is illuminated, it changes color, as you see here. And when illumination is stopped, then the material will be bleached again into its original state. Originally, transmittance of this coating before illumination is on can be very high. It can be between maybe 75% up to 90%. One can control it by controlling the deposition process. After illumination is on, depending on thickness of the film, depending on deposition conditions, one can get different contrast. So after, for example, half an hour illumination, transmittance can be reduced from maybe 80% up to 40%. If illumination is not just half an hour, but more, then this transmittance can be further reduced up to 20% or even 10% until the window can become very dark. Advantage of this material is that when illumination is stopped, then it will be bleaching back into its original state. One can get that material by several methods. One is vacuum-based method. Example is here magnetron sputtering. In the magnetron sputtering, in the hydrogen atmosphere, yttrium will be deposited on substrate, and then one can get yttrium hydride that is of black color. And after oxidizing, that will become transparent to visible light. Oxidation process can continue just 2-3 minutes. And then the other method of getting this oxyhydride is chemical method. The physical method of obtaining the material is very expensive and it's time consuming. The point is to get high quality thin film, photochromic film, one should first create vacuum in such a magnetron sputtering machine. The larger the machine, the more time consuming is the vacuum creating process. After vacuum is created, then one should do the deposition. So a lot of time will be spent. In addition, the large magnetron sputtering units, they will consume a lot of electrical energy. And one example, vacuum-based method, chemical vapor deposition, for example, it consumes at least 4 times less electrical energy than magnetron sputtering. So because of that, it's always interesting to search for alternative methods of deposition of high quality materials by low-cost method. The low-cost method is chemical, of course. Here is one of the examples of obtaining photochromic powders. And the photochromic powders in this case has been obtained by hydrogenating metallic yttrium particles. And then by ball milling, metal hydrides have been obtained. And then these metal hydride powders have been oxidized. And then by this way, metal hydride powder, metal oxyhydride powder has been obtained that possess photochromic properties. As you see the picture here in the middle picture, this powder has been illuminated with UV light, and then this illuminated part became dark. After about half an hour, it has been bleached. Once one gets this type of powder, afterwards one can incorporate them inside polymer, and then one can get hybrid or composite material. Then, of course, transmittance of the material will be too low, but by applying a post-processing procedure, one can enhance photochromic performance of the powder for the hybrid film. Alternative chemical method is one can use yttrium oxide powders and reduce it in low-cost metal hydrides. This is even much more cheaper and much more efficient than ball milling powders, in the sense that in the ball milling powders one should use pure yttrium, and yttrium is just very well oxidized once you open the bottle containing yttrium. For this reason, it's very efficient to use yttrium oxide, because for purification of and the yttrium, one can spend again a lot of effort and energy and time, whereas yttrium oxide is widely available. And then if one reduces it in the different metal hydride environment, one can get yttrium oxyhydride. Of course, it will not be pure as thin film is deposited by vacuum-based methods, but it will be low-cost photochromic film. Now, let's talk about parameters characterizing photochromic films. Both transparent state and photodichromic state, they will be characterized by transmittance spectra, as I showed you in previous slides. Here also, and then absorbance spectra, reflectance spectra can also be used for characterizing photochromic films. Then the other parameter is color change time, or what we call coloration time. When sunlight is falling on the transparent film, color changes. The point is how fast it's changed. This is important. It's very good if color change will take just maybe a few seconds. And then bleaching time. This is another very important parameter. In the practical application of photochromic coatings, bleaching within just few seconds is very important. It shouldn't be minutes, it should be seconds. So this is another requirement. This is a requirement provided by the market. So then task of scientists is to tune materials properties by applying different methods. For example, by doping or by tuning material synthesis method and so forth. There are many ways of how to do it. Then another very exciting parameter is it's cyclic testing. Cyclic testing, it means material will be illuminated within half an hour, then light will be switched off, another half an hour to let the system to bleach back into transparent state. and then illuminate it again, and then bleach it again. So this process should be continued multiple times. So before bringing this material into the market, this type of testing must be done. And if as a result of the illumination, if transmittance corresponding to a transparent state will decrease with time, and contrast if changed, then it means the material is not ready to bring it into the market. It should be constant like this, more or less, so that material's property, it should be guaranteed. Then only one can bring it to the market. Suppose we solved all these cases. What else? The next step is to create prototype window and then perform testing. Whether color will be the same after several times depositions. For example, we will prepare like 100 such coatings on different, and whether color will be the same, transmittance will be the same or not, and whether bleaching time, color changing time is the same or not. And this, it should be tested. Afterwards, after the success, and then next stage of testing will happen. It is in climate chamber, when temperature of the environment will be tuned, illumination intensity will be tuned, and then when that process is finished, then outdoor testing should be performed either. And for outdoor performing, one can create just some site for for installing the prototype windows, or demonstration house better. So after all these testings are successfully done, then only one can think about commercialization. But before commercialization, one should be sure about price, about toxicity testing, how safe the material is. If one is dealing with very safe materials like zinc oxide or silicon, it is good, it's safe. But if you are dealing with new material, and if it is nanomaterial, then one should keep in mind that with changing size, dimensions, toxicity will also change. So this is very important point to check toxicity. And the circularity is very important. Life cycle assessment is very important. There are many important points. Okay, why we should perform all these testings? Why we are interested in this material? So we are mostly interested in window applications. However, window application is not the only one. For example, why windows? When it is too sunny, for example, when one cannot see what is ongoing outside, then the natural reaction is to close the window by using curtain. And when you have photochromic coating, then there is no need. And this type of window is for creating comfort to people, and just to block this ultraviolet light irritating human eye. It would be very good, of course, if one blocks also heat waves, if heat transfer through window will be reduced as well. For that, one can just deposit one more layer. For example, silver coated, very thin layer of silver, or transparent and conducting film could be another useful case. Then other applications include goggles, for example, and automobiles. And here you see the example of using on the photochromic coatings in goggles. And it can be used as photochromic lenses as well. And here are some examples of using photochromic coatings in automobiles, for example. Of course, in case of front window applications of automobiles, one should follow country's regulation. In Europe, it's not allowed if front window transmittance is less than 85%. And then color change should be very fast. Okay, and then in conclusion, so photochromic coatings is one of the very important coatings at present that and there is strong demand in such coatings. And the materials, the coatings have many applications, not only in building windows, but also in automobiles, on side windows of automobiles, on a roof window of automobiles, for example, on displays, and on making masks during some experimentings or materials preparations, and then also as storage devices as well. So this is briefly about photochromism. Thanks for attention.